cold season. Cold season in Brazil.
Summertime now.
Yeah.
Starting summertime.
Actually, this is rainy season. This you can say. And after from October onwards, it will be cold here over here.
Wow.
Just opposite to the Brazil. Yeah, I think.
Yeah.
Because when I supposed to come to the Brazil, I look at the weather over there. So I could understand on that time that the weather is that just opposite between Brazil. So I think 34 participants have been joined, and some of the participants used to watch your video through YouTube, sir, because we make it online via YouTube channel. So some of the participants used to watch the streaming video via YouTube or sometimes Facebook, something like that. So I welcome you again today, Professor. It's my pleasure that you are here with us, and we will be getting benefited from your knowledge. And I request you to start your presentation. Welcome, Professor. Over to you.
Okay, when you want, I can start.
Yes. Hello, Professor. I think you can continue. You may continue.
More 5 minutes?
No, Professor. I think you may start now.
Okay. Well, let's go. Well, thank again, Anup, for this kind invitation to give the second lecture. And the lecture today will be about different material from yesterday. Yesterday, we talked about some biological fluid, which was basically water solutions of LDL particles that we find in our blood. And today we will speak about magnetic nanoparticles in not only optical absorption, nonlinear optical absorption, but also the nonlinear index of refraction of these particles. Some of the collaborators are quoted here. The work was done here in the University of Sao Paulo, but we have more collaborators, and one of them is from India, Kinari Parekh, which came to our lab as a visiting professor during 3 months. And we did a lot of work with her. She made many different cubic nanoparticles for us to investigate the nonlinear optical properties of these particles, compare it to spherical particles. It was a very nice collaboration that we believe that we can continue in the future. Well, this is the outline of the talk. And the first thing, we will define the magnetic nanoparticles, and we will see how they respond to the application of an external magnetic field. After that, we will talk something about the nonlinear optical properties, basically the electronic lens that I mentioned en passant yesterday. So the laser that we will use to put in evidence this type of nonlinear optical properties must be a pulsed laser with femtosecond pulses. We will discuss the Zscan in this different time scale from yesterday, and another technique that we use to measure also some nonlinear optical properties, which is the hyper-Rayleigh scattering. So I will introduce this new technique to you, and we will basically investigate the possibility to have anisotropies in the third order susceptibility, Chi3, and the first hyperpolarizability, beta. The third order susceptibility will be obtained by using the Zscan technique, and the hyperpolarizability will be available to us using the hyper-Rayleigh scattering. Take the conclusions and finally the take-home message. Well, when we speak about magnetic nanoparticles, let us discuss the different types of nanoparticles we have. We are speaking about a colloidal suspension of small particles with typical dimension of about 10 nanometers. So this is the core of the particle in red here. And if you have just these particles in water or in oil, what you have is a phase separation. The solvent will go to one side and the magnetic nanoparticles go to the other side, due basically to the attraction, the van der Waals attraction, and the dipole-dipole, magnetic dipole-dipole attraction. To avoid the phase separation, water from one side and magnetic nanoparticles from the other, we have to introduce something in the surface of the nanoparticles to keep the colloidal suspension stable. This here, for example, I'm representing the molecules of water, and I want to put this magnetic nanoparticles in a polar solvent. So how I do that? I put some charges around the particles. I charge the particle with a positive or negative surface charge. Obviously, we have counter ions in the fluid. Outside is not shown here in this picture, but you have now the possibility of a repulsion, electrostatic repulsion between particles when they try to come together due to the van der Waals or the dipole-dipole interaction. So when we charge the particles, it's possible to have a stable colloid. So the particles now will be completely stable, the colloid will be stable, and we can put this, for example, in water. What we can do also, instead charge these particles, we can put amphiphilic molecules around the particles. So here is one amphiphilic molecules and the other one with the polar head at that position, polar heads of the amphiphilic molecules there. So you can put this particle in water and you have a steric interaction between the particles, so they could not occupy the same volume. So when the van der Waals interaction and the dipole-dipole interaction try to put the particles together, the interaction between these chains here will give some type of repulsion between them, and you have the colloidal stable. So with this double surfactation, because we have one amphiphilic molecule here and another amphiphilic molecule here, so in each part, in each side of the particle, you put essentially two amphiphilic molecules, one like that and the other like that. So the polar head attached to the particle and the polar head here will be in contact with water that's a polar fluid. Well, but I can also put these particles, stabilize these particles in a non-polar solvent, for example, in oil. In many transformers for electricity, we have this type of particles suspended in a non-polar fluid, and what we have now is the simple surfactation. Here's the polar head attached to the particle. This is the carbonic chain. And the carbonic chain, you can put, for example, in a non-polar solvent, it will be, again, a stable colloidal suspension, because when the particles tend to attract due to dipole-dipole interaction or van der Waals interaction, the steric repulsion between them will keep the particles stable in the non-polar solvent. So we can put these particles, nanoparticles, from about 2 nanometers to about 15 nanometers. You can stabilize in different types of fluids, polar and non-polar. and they are absolutely stable. And each of these particles, they have a magnetic moment associated to the structure of the particle. So when we put a magnetic field, an external magnetic field, you can have this type of figures. Now you have a ferrofluid with the magnetic field perpendicular to the free surface of the ferrofluid. So this is the magnetic colloid, stable in the presence of air. So air and magnetic fluid above, below, and you put a magnetic field perpendicular to this interface. So this is the type of spikes that are basically the Rosenzweig instability that appears. And these are essentially the behavior of these ferrofluids in the presence of an external magnetic field. If you try to see this in an electronic microscope, you can have different types of particles. For example, here you have almost spherical particles, okay? The typical dimension here is 100 nanometer. So the typical dimension of the particle is about 10 nanometers, 12 nanometers. You can have cubes also. So Kinari, Parek did the synthesis of these particles, which are cubic, and we investigated, we compare the nonlinear optical properties and structure of these cubic particles with respect to spherical particles, essentially with the same base of composition. And you can have mixtures also. You can have different types of shapes and spheres, cubes in certain parts. So in principle, you can have a very nice chemistry of these particles, and depending on the application you are interested in, you can make different types of particles and synthesize them and investigate with different types of condensed matter techniques. So basically the structure of these nanoparticles, named the spinal structure, direct spinal structure, may be also inverted spinal structure, where you have, for example, the iron here in the tetrahedral symmetry or octahedral symmetry here, and you have a super paramagnetic material. So we don't call this a paramagnetic material because paramagnetic is essentially used when you speak about spins. But in our case, we have a bunch of spins that together gives a neat different from zero magnetic moment. So is a big particle with respect to the electron, for example, it's a big particle with a magnetic moment on it. So we call this a super paramagnetic material. And this magnetic moment can be, we can play with it, changing the direction of the external magnetic field. And if we look in the electronic microscope, we make electron scattering, we can show that there is a structure. This is the structure inside one particle. So imagine that you have one particle of this ferrofluid, and we are observing by electron diffraction, the organization of the atoms inside one particle only. So you can see here the periodicity you observe in electron microscopy and the electron diffraction, and the magnetic moment will be pointing from this atom here to this atom there. So along the main diagonal of the cubic structure, of the spinal structure. So if you take into account that these diffraction rings, the electron diffraction, you can have information about the local structure inside just one particle of this ferrofluid. I didn't say, but this magnetic colloid is also named a ferrofluid. When you have charges around the particle, you call this an ionic ferrofluid. When you have amphiphilic molecules attached to the surface of the particle, you have the surfacted ferrofluid. Double surfactation to put in water, and simple surfactation to put this in nonpolar solvent. Well, so these nanoparticles are essentially magnetically uniaxial. So there is a magnetic moment attached to each particle. And one question that we will respond by the end of, almost the end of this talk, is the question, is there an eventual anisotropy in these nonlinear optical parameters, chi3 and beta? Remember that chi3, I will show you in more details, are basically the third order susceptibility of this material. And beta is the first hyperpolarizability. So two types of parameter that characterize one particle, and we will see what happens if this has, despite the fact that it is uniaxially, magnetically uniaxial, if there is an anisotropy in this parameter when you investigate along the magnetic moment direction and perpendicular to the magnetic moment direction. So this is what we'll try to investigate now. We have a lot of questions about basic science, essentially to understand the structure of this material. So this type of study give us basic science information about the structure of the particles, the organization of the atoms, the different levels of the electronic structure of the material, but also we are involved in applications, because depending on the direction of the electric field with respect to the magnetic moment of the particle, you can have different types of absorption. So it absorbs more or less depending on how the electric field and the magnetic moment are aligned. And the magnetic moment, you can vary the direction of this by applying an external magnetic field. So for example, for transmission of information, it should be interesting if you want to get rid of one of the polarizations of the light. You can, for example, orient your magnetic particles along the direction of mu, and the electric field of the light, for example, in an optical fiber, or perpendicular to it in an optical fiber. So you can have some applications trying to control the absorption, the nonlinear absorption of these materials acting with an external magnetic field. Well, so it's very interesting how the system responds to external fields. There is one critical field, so this I am representing the magnetic field, which is applied along this direction. So if the field you are applying is smaller than the first critical field, what happens is essentially the orientation of the magnetic dipoles preferentially along the direction of this field. There's no formation of aggregates if the magnetic field external applied to this system is below this first critical magnetic field. If you increase the field for one which is in between the first critical field and a second critical field, what you have is basically more than the orientation, you form clusters. You form basically lines like that, linear aggregates with the magnetic moments oriented along the magnetic field in mean, okay? The mean orientation is this one. And if you increase more the field, you will reach a second critical magnetic field when you have this type of structures forming bundles. So you aggregate these lines, these linear aggregates, forming this type of structures where the magnetic moment of each particle basically are pointed along along the external electric field, but they are now forming a bundle. This type of structure may be seen even in optical microscope. So this type of thing can have on the order tenths of microns. And in some conditions, it's reversible. In other conditions, it's no more reversible. For example, if you modify a lot the type of covering you have around the particles. You can modify this cover and the particles will attach to each other and you can no more remove these bundles which are formed in ferrofluid. But if you make this, increase the field, and after you load the field, in principle, this behavior is reversible. Well, so as we discussed yesterday, we are now speaking about nonlinear optics, but it's a nonlinear optics in a different time scale. We are not interested in modification of the temperature of the sample because the process that we will describe now is a very fast process of the order of time, typical order of time. Time scale is about femtoseconds, 10 to the minus 15 second. So if you have a material that you put an electric field on it, we see that the polarization is proportional to the electric field. This is what we learn in the basic physics course in the university. The polarization is proportional to the electric field. So if the field now is high enough, as we saw yesterday, what is this? Polarization is now, sorry about that. This polarization now has other terms, high order terms. So the polarization is proportional to the electric field. The first order susceptibility is proportional to the E square times E. E is the electric field, and this is the frequency of the electric field. So this is the first order susceptibility, second order susceptibility, third order susceptibility, and so on. Depending on the strength of the intensity of the strength of the electric field, you can have more terms in this written of the polarization. So different susceptibilities occurs, different orders, and these susceptibilities are determined essentially by the symmetry properties of the medium. If your medium has symmetry like a mirror symmetry, for example, if you are in a point, what you have in one side is exactly what you have in the other side, this chi2 by the symmetry reason must be zero. So if you have something which is isotropic, like the ferrofluid, without the magnetic field, you have this chi2 equal to zero. So the first term in the expansion of the polarization as a function of E is the third order susceptibility. So the nonlinear index of refraction has this linear contribution as we saw yesterday, and we have the nonlinear contribution here, where this N2 is essentially the nonlinear index of refraction. And you see that here is the intensity of the beam, intensity of the light, the laser in this case, which has been used to measure these properties. So if the intensity is high, you have this term that contributes with the linear index of refraction to give the total index of reflection of the system. And what we will measure basically is this N2 term that is related to chi3 in the case of ferrofluid, because the ferrofluid is an isotropic solution without the magnetic field applied. Well, if you think about polarizabilities, this is the energy of a dipole moment in the presence of electric field. So this is the dipole of your particles, for example, which is formed here, and this is the electric field of light. So the energy of this material in the presence of light depends on this angle, certainly. So has a term which is the linear one. This is the dipole moment, so which contributes to this energy piece. Is the tensor. You need to put it here, a vector here in this case, but here is the tensor, the polarizability, and the first order hyperpolarizability. So this is the term that I show you in a while, that we have a technique to give us this information. So this is related to the energy of the dipole when you put the dipole in the presence of a strong enough electric field. So what we will discuss in the following is the measurement of chi3 and the measure of the first hyperpolarizability. And this will give us information not only from the basic point of view to understand what is the arrangement of these atoms and electrons in the structure, and also for some applications in the case of optical fibers and transmission of information. Well, so as I told you, the electric susceptibility, this is the first term of the electric susceptibility, the first order susceptibility, the first susceptibility, and you can write this in a tensor form. This is the second order susceptibility, so the second contribution to the polarization. In the third order susceptibility, you have these different tensors which are present. And for example, this is the three principal polarizations along the three orthogonal axes in the laboratory frame axis system. You put, for example, a magnetic field along one direction, and you can measure what happens in this direction and in the plane perpendicular to this direction. So this is what we will do in the following. And you see here, this is the intensity of the laser beam interacting with the magnetic particles. So this will be the thing that we will measure using our experimental techniques. Well, as I told you yesterday, depending on the mechanism you are interested to investigate, you can have different time scales. So please look at this column here and this column here, okay? So the mechanisms can be the electronic polarization. You see that the time scale here is femtosecond. And if you are interested in investigate how the electrons respond to this electric field coming from the light and the photons which interacted with these electrons, you have to take into account the time scale of your experiment, 10 to the minus 15 femtoseconds. The molecular orientation are 10 to the minus 12. Electrostriction, saturated atomic absorption, thermal effects, which we discussed yesterday, to milliseconds, what is happening now, that we discussed yesterday. Pulse lasers of milliseconds are enough to see what is going on with the modification of the temperature of the sample. And as I told you yesterday, we have in the time scale of 1 second, the Sorey effect. The Sorey effect is something like that. Imagine that you have one sample here, the magnetic nanoparticles are distributed, and I am shining this particular colloid with a Gaussian beam. So this is the profile of the Gaussian beam. So the temperature in the center of the beam is more intense than in the borders. I don't know if you can see, but this more red here in the center tries to identify a region which is hotter than the borders. So if we leave this particular beam for time scales of about seconds, what you see is this type of behavior. So the particles will, in this case, go to the hotter part or go to the other part, colder part of the beam. So when the particles go to the colder part of the beam, we name this a thermophobic ferrofluid. And when the particles go to the center of the beam, which is hotter, we name this a thermophilic ferrofluid. So this, in particular case, is the thermophilic ferrofluid, where when we shine light for time, reasonable time, for example, 1 second, 2 seconds, these particles slowly go to the hotter part of the beam. We have both types, thermophobic and thermophilic behavior in different types of ferrofluids. Well, as just to remember you what we saw yesterday, if you have nonlinear optical material which interacts with this particular Gaussian laser beam, more intense in the center of the beam, less intense in the borders. This is the profile of the beam. This is the plane waves which reach the sample. If the sample has no nonlinear optical response, they will transmit basically the same type of plane wave here. But on the other side, if you have a nonlinear medium here, the speed of light depends on this particular nonlinear optical property of the medium. Yesterday, we discussed the thermal effect. So thermal effect means that you have essentially different temperatures in the center of the beam and in the borders of the beam. But if you have a very fast pulse, we have no time to make the diffusion of heat, and neither increase the temperature, because you have, for example, one pulse, you wait some time, another pulse, you wait some time, and this pulse has the width of about femtoseconds. So it's not a thermal process which takes place here, but it's basically the electrons go from one level to the other level, and after that decay, and you have the self-focusing process and the self-defocusing process. So your medium here, in the case of the ferrofluid, will act like a convergent lens or a divergent lens, but not a thermal lens. There's no thermal involved in this process. It's basically a lens formed by this population of electrons, which go from one level to the other and come back. So this response is nonlinear and makes your sample behave like convergent or divergent lens. Well, let us see what is this nonlinear absorption, what we know about this process. So there is a two-photon absorption, and to understand this, imagine that you have a ground state here, so your electron is here, and the energy of one photon is not enough to take this electron from here and populate the first excited state. Imagine that you have a photon that does not have this enough energy to take one electron from here and put an electron here. But if the intensity of your beam, so the quantity of photons you have, are so high that your system can absorb two photons. And when the electron absorbs these two photons, it's possible to go from this level to the other level. So the difference of this energy from the first excited state and the ground state is about twice the energy of one photon. So the absorption now is the linear absorption that we know usually if the electric field, if, for example, the photons are not enough to produce this type of process, the absorption is only the linear part. But if the number of photons is so high, you have a nonlinear optical absorption, which is this beta. This beta is also related to the imaginary part of chi3. So we are able also to measure this parameter here, measuring the third order susceptibility. And the cross-section for this two-photon absorption here, this is the energy of one photon. This is the absorber's density that you have in your sample. So beta is directly related to the cross-section for this process. So if we measure chi3, we have beta. If you have beta, you have this cross-section, second order, the two-photon absorption cross-section for the process that I described here. But you can have another type of absorption, which is also nonlinear. Imagine that you have an incident beam here, okay? Your sample there, and you have the fluence incident and the fluence outside after your sample. These are some equations, which is not so important at this level, but what is happening is the following. Imagine that you have one state, a ground state here, and you have a band at that position. So what happens is that the free carrier absorption is an electron which is in the band, absorbs one photon and goes to the other level inside the band. And you can absorb a lot of photons in the band. And this absorption, if you have here the transmittance of your sample as a function, this is the Zscan experiment. I'm putting this now, but we will discuss in more details in a while. So, oops, sorry. So if we have a decrease of the intensity of the fluence after the sample, when you pass through the focus point of the laser beam, the Z-scan scattering, the Z-scan experiment, you have basically this free carrier absorption. And the free carrier absorption has a cross-section also, and this cross-section we can also measure using the Z-scan experiment. Well, just to give you some bench of sample, we will discuss properties which are very general, but just to give you an idea about some different types of ferrofluids we investigated. For example, for this magnetite here, Fe3O4, which is the core of the particle is this F3O4. This is a simple surfactation, and we can put this in a nonlinear fluid like oil. This is the double surfactation. We can put this in polar fluids like water, and we have different types of them. Liquid carrier here, thickness of the layer that we can put to make some films, okay? The concentration in volume percent of particles in the fluids. So we investigated a lot of these materials, not only this one, but just to give you some flavor of what type of material we are studying. And the temperature, as I told you, is a super paramagnetic material. So we are above the block temperature. So the block temperature is very low in this material. So we are at room temperature, at least in Brazil. We are in the super paramagnetic state. So the magnetic moment is there, and we are able to change the orientation of this magnetic moment as a function of the orientation of the external field. Well, the Z-scan, as we discussed it yesterday a little bit, this is the focus point. You have some geometrical parameters here. So imagine that you have your laser in this side of the figure. There is a lens of glass. It will focus in a particular point and will after increase the dimension of this beam until the detector. So all these parameters here are determined geometrically. So always that you see this type of symbols in the equations is something that you can have geometrically. It's not something that you can measure in your experiment. You make your experiment with these geometrical parameters. And as we saw yesterday, you have a laser beam here, you have a lens, will focus in a particular point z equal to 0, and we will scan the sample along the z direction. You have a detector here, and you have an iris at that position. So depending on the intensity of the beam, so the intensity here is lower than here, which is the higher intensity we have, we concentrate the energy at that point. After we open and we measure just what is entering in this small iris in front of the detector. So this is the Z-scan that we will discuss now in the case of femtosecond lasers. So if you have your sample, which has this type of behavior, for example, if you are in the left side of the focus, you see that you have a defocusing behavior at that point. So the intensity you have here is smaller when the sample is far from the focus. When you cross the focus, you concentrate the energy here in the iris. So basically what you have here with hands just is a normalized transmission as a function of the Z position. If you are in the left side of the focus, you have a decrease of the intensity in the iris. And after that, you have an increase when you are after the iris. And when you go far from the focus, you have, again, normalized transmittance equal to 1. So basically, this is a Zscan measurements in different time scales. If you have a convergent lens, you have this type of behavior, valley to peak. And if you have a divergent lens, you have a peak to valley. So just looking at the figure you have in the Z-scan curve, you can see if your sample behaves like a convergent lens or a divergent lens, just expecting this type of curve in the Z-scan experiment. So in our case, as we are interested in electronic process, the laser here is a femtosecond laser just pulsed. We have pulse of about 196 femtoseconds. After that, we put a pulse speaker here to reduce the number, the peak, the high of the peak. We put a shutter here to just remove even these small peaks here that could hit the sample, and I'm not interested in the thermal lens. I don't want that the thermal lens be formed in this sample. So I cut completely the laser with the shutter. After I open again, another peak of 196 femtoseconds. I cut with the pulse speaker and the shutter again, and this goes on. So I will investigate pulse by pulse. Okay, so this is a very interesting measurement that we, oops, sorry. It's very sensitive, this mouse. So what I investigate is pulse by pulse. My detector here is able to detect, is a very fast detector, which will detect to us the behavior of this femtosecond pulse. And we take one by one, we change the position of the sample along the z-axis, passing through the focus point. And what we have here is a mirror that leaves past part of the intensity, and part of the intensity goes to this lens. Here is a glass lens, which put all the energy here. So in the same experiment, I can measure the real part of the index of refraction. So the real part of chi3, which will give the nonlinear index of refraction, and the imaginary part of chi3, which is related to the absorption, nonlinear optical absorption. So here I make the measurement of the absorption, and here I make the measurement of the diffraction. The wavelength we use is very important to choose the good wavelength which will be absorbed by your sample. You remember that when you are speaking about the 2 photon absorption, this energy of 1 photon here must be essentially in the middle of the gap between the ground state and the first excited state. So I can tune this lambda, this energy of the photon in our laser. It is a tuned laser. It's named chameleon because you can have different colors of the laser, different energies of the laser. So we tune this to be exactly in the middle, in between the ground state and the first excited state, to be sure that what we will have is a 2 photon absorption. This is the intensity of the beam. As we saw yesterday, must be a very high intensity of the order of 10 gigawatts per square centimeter. And this is the parameter I showed you before, is basically the width of the beam in the position of the focus, okay? And the second experimental setup that we use it now to measure the hyperpolarizability is the named hyper-Rayleigh scattering setup, which is basically a pulsed laser here also. This is the type of pulses that these lasers will give, okay? This is the pulse number of pulses, and here is the intensity. So you have a lot of pulses here of the order of 30, 100 picoseconds, 100 picoseconds Q-switched envelope, having about each one 170 nanoseconds. So what we have here is basically the laser. Go to the computer. There is a lens which opens the beam. This is basically the reference will come to us. These two lenses at that position, which will converge at that point. So when the laser is shining the sample is in the position B. The line here will tell you that the sample will be illuminated by this Antares 76X laser, and it will produce photons of different energy. So we are entering here with a lambda of 1064 nanometers, and we will take here in the photomultiplier the lambda 532 nanometers. So you see that this is basically a second order with respect to this one. So your sample will absorb these photons and will emit a different photons here with this wavelength, and the intensity of this second order photon, which will be emitted by the sample, is proportional to the intensity, the inside intensity of the green light, of the red light here. There is a geometrical parameter, the number of emitters, and here is essentially what we are interested to measure, which is the hyperpolarizability. Okay, so if we measure this we have, this is a geometrical factor. We know how many absorbers or how many emitters you have in your sample. This is basically one fitting parameter to this simple expression here. So it's very easy and very precise measurement of this parameter beta. Well, so let us try to see now what happens in terms of linear optics in the beginning. This is essentially the absorbance, linear absorbance as a function of the wavelength. As I told you, we are able to tune our laser to, for example, 800 nanometers, which is in that position, or we can tune along all this wavelength interval, depending on which physics we are interested. So imagine that we are putting now our ferrofluid, a magnetic field of this intensity here to 1700 Ørsted, and we are observing here the electric field of the light parallel to the magnetic field and perpendicular to the magnetic field. If we are using unpolarized light, is this continuous curve black here, okay? If you are in the condition perpendicular to the magnetic field, you have almost the same result. However, if you are parallel to the magnetic field, you see that the linear absorption already is higher with compared to the perpendicular orientation or even the non-polarized ferrofluid. So we take this into account and we will fix our experiment in lambda equal to 800 nanometers. So these are the typical results of the Zscan. Normalized transmittance as a function of the Z position. So you see here already that you have the typical convergent or divergent. You remember that just inspecting this, you have this information of the type of lens which was formed. This is a fitting of the model we have, was developed many time ago by Sheikh Bahai. We make some improvement of this in 2003, as I showed yesterday. And this is the absorption, normalized transmittance as a function of the Z position. And you see that when you are far from the focus, you don't have essentially any effect. But when you approach the photons, the absorbance increases. So you have a less intensity of the beam when you pass through this focus point of the laser beam. So these are basically the curve or the model we fixed. This is the closed aperture is essentially this curve here. And the unique parameter you have to fit is N2. So it's 1 fit parameter. All the other things we know from previous measurements or the geometry of your sample. And the red curve here is related to this transmission, the normalized transmission here, which the unique parameter you have is beta. So it's a very strong type of fitting. And from this, we have beta and we have N2 also. So we have N2 and have beta with both type of experiments. This is for the detector in the Z direction, and this is for the detection of the other detector, which was separated by the beam splitter. So with one experiment only, we have both the transmittance and the reflection of the sample. Well, this is for H equal to 0, okay? But we can make the same type of measurements, the Z-scan. Now, we have a polarizer here, and we can put the direction of the electric field parallel to the magnetic field or perpendicular to the magnetic field. We can control with this polarizer here. These are two magnets, two permanent magnets, which gives a field here of about 2,700 Ørsted. We can vary the distance between these two poles and increase the field from 0, from the field of the Earth, for example, until this higher magnetic field we have. And all this setup changed the position with the sample. So all of this is now over this rail, and we can move all this setup along the Z direction, and we measure the Z-scan in the presence of the magnetic field. So these are, again, the typical results we have for the absorption here, for different types of magnetic field parallel to the electric field of the light, perpendicular, different types of ferrofluids. And also this transmission here, we can measure the alpha. So is the cross section for the 2 photon absorption, which is related to beta. You remember, no? So this also is another type of fit that you can do directly from this type of measurements. And you can have not only the nonlinear absorption, but the alpha, which is the essentially the cross section for the 2 photon absorption, the process. Again, here you have the different types of N2. So N2 is what you have for this type of curve, and beta from this one. I don't know if you are able to see, there is a small difference here. If you see, for example, the squares and the circles here, you see that squares are more deep than the balls, the circles, because one of them is the orientation parallel and the other perpendicular to the magnetic field. Or in this case, for example, if you have no field, is this circles here, and when you put the field in the direction parallel to H, you see that the square has a valley which is more deep than the first one. Well, so let's put all this together, all these results together. We are investigating the 2 photon absorption. So here is the cross section for this 2 photon absorption in this unity. That's very strange, but it is, oops, it's not important now. I'll give you the order of magnitude in the following. So here is the measurement of the electric field parallel to the magnetic field. So the electric field of light parallel to the magnetic field. So the particles are oriented with the magnetic moment parallel to the electric field of the light. So you see that when you increase the magnetic field, this axis here is the magnetic field increasing, and here you have basically the cross section for this 2 photon absorption. If you are perpendicular, so the magnetic moment and the light are perpendicular, when one with respect to the other, we almost don't have any modification, significant modification. But when you are seeing what is happening, when you increase the magnetic field and the light, the electric field is parallel to this field, so parallel to me, you have an increase, more significant increase of the two-photon absorption with respect to the increase of the magnetic field. So here we are able to put this more than 3,000 Earths here. Here also for the magnetic field increasing, different types of ferrofluids. If you are parallel, you are almost at the same place. If you are perpendicular, almost the same place. If you are parallel, you increase more. So you have an anisotropy of this two-photon absorption cross-section in a system which is basically uniaxial. So what we can have with this, I told you that the GM is named the Gerd Meyer, the name of this unity, okay? And 1 GM is 10 to the minus 15 centimeter to fourth time second per photon. So this is the number, as I told you before, I showed you before. This is the beta as a function of the number of observers, for example, for this particular ferrofluid here. So if you measure for different types of concentration, of different concentrations of magnetic nanoparticles, you can measure beta as a function of this, and the slope of this curve here, will give you the sigma for the two-photon absorption in different conditions. This was the energy of the photon we used there. So this is basically what we are able to do to measure the sigma I showed you before in this graph here. So always looking at this type of core of nanoparticles, always magnetite we are observing, about 10 nanometers of diameter, typical diameter. We could put this like oil, like acid coated in water. And what we can see here, please look at these numbers essentially here. Oops, sorry. Here you have the sigma two-photon absorption for H equal to 0. So all the magnetic moments are oriented, randomly oriented. So you have this for when you put zinc. This is not an important point. I just see when you have this without a magnetic field, you have this type of numbers for the sigma. When you put this field in the parallel condition, so the magnetic moment, the field, and the electric field of light, all of them parallel, you have this type of numbers, about 21 here in this GM unities. And when you go to the parallel configuration, so magnetic moment, magnetic field, and electric field of the light perpendicular to this structure, you have a smaller two-photon absorption here. Okay, so this anisotropy we are seeing here is measured. Now we can measure this anisotropy in this parameter, sigma, and this anisotropy is, we will see, let me pass, this is not so important. There is an anisotropy that we are able to measure. I will tell you in a while. Well, let's see another type of nonlinear optical process, as I told you before, is the free carrier absorption. So remember that you have the ground state, you have a band here. So who are absorbing the photons are the electrons which are in the band here. There's not unique levels, but just a band. So one electron absorbs the photons, and this is a nonlinear optical process because you have a lot of photons available to electrons. So the free carrier cross-section that we are able to measure in the case of this ferrofluid is this. And if we compare to the bulk material, the cross-section, the free carrier absorption cross-section is small. So probably what we are seeing here is a signature of a quantum confinement. You are now observing a sample which has about 10 nanometers of typical diameter, comparing this to a bulk. A bulk is an infinite medium. So when you go for an infinite medium, magnetite, for example, the particles with typical size of microns, for example, or centimeters, and you compare to the particles which has about 10 nanometers of typical diameter, you see that this sigma is different. And probably this is something we are speculating now. We don't have more information, but the difference between these two numbers probably are giving us some information about what we could name the quantum confinement of this electronic structure, which are basically reduced in volume. You have now a very small particle you compare to the bulk. When you confine this, you have a layer around the particle. So this new structure gives us a new type of electronic arrangement of the band and the ground state in the particles. And this gives us some information. So it's something that we have to continue to investigate to have more information. And as I told you that we are speaking about the arrangement of these ferrofluids, it was important to see which type of structure we have when we put the magnetic field of the order of magnitude we are using in our experiment. So to have this type of information, we use the small angle X-ray scattering. This is the machine we have in our lab. We have two machines like this. It's a multi-user machine, so everybody around the world can apply to use this machine in our lab. So we have different types of X-ray wavelengths, chromium, molybdenum, and copper here. And we can, for example, go to very, very small angles, which is very important to determine the structure of this type of colloids. So these are the figures we have. Basically, the X-ray is going through you to the display here. And if you don't have a magnetic field, you have an isotropic band around the center of the beam. So the beam is here, sample here, and we are seeing what is the small angle scattering in a plate. And when we put the magnetic field along the X direction, is this direction, the horizontal direction, you can see also a modification of this pattern. You see that you have two bands at that position. Here you don't have the bands, so there is an anisotropy when you put, for example, a field of about 1 kilohertz. We use it until 3 kilohertz. So take into account the X-ray data we have, we could make a model of the particles in our study. If the field is not present, the particles are absolutely free to rotate. But when we put a field of about 2,000 Ørsted, 1,000, 3,000, in this range, what we have is this type of structure. The X-ray gives us an information about this dimension of the aggregate, which is about 7 nanometers. So it's typically the diameter of one particle. So you don't have one particle over the other in the vertical direction, because this is the X-ray results. And this dimension of the aggregates we got from the X-ray is about 36 nanometers. So you have about 5 particles oriented like this. And so all the results we got until now with all the techniques I show you, in all the results for sigma, for N2, for beta, all of them comes from this type of structure when the magnetic field is present. And we are seeing this with the electric field parallel to H and the electric field perpendicular to H. So this is essentially the type of structure which are present in our colloidal suspension as a function of the magnetic field. So we are in between the first critical field and the second critical field. We don't have free particles, but we don't have neither bundles formed, okay? A lot of these lines, aggregates forming very big, big aggregate bundles. We have this type of structure only. And also the magnetic moment here is oriented along the 111 direction, the spinal structure. This we had before. Well, so as I told you, we are able to measure the imaginary part of chi3. We measure also the real part of chi3. And for h equal to 0, the imaginary part of chi3 is here. So these are typical values of this materials. It's interesting to tell you that when we put the magnetic field, we fix one direction, but we cannot fix the two other directions perpendicular to the magnetic field. So the particles can turn around the axis of the magnetic field. So the chi3 in the direction of the field, we are able to measure, there's no problem, but perpendicular to the magnetic field, we don't have the possibility to fix the second axis. So what we measured here is a mean value between the two third order susceptibilities along the y and the z axis. The x-axis we are able to measure because we fix the direction along the magnetic field. But the other one, we measure this number, which is, we can assume that, for example, is a mean value of these two. If we assume that they are not so different, we can have the measurement of the, we can make a mimic of what happens if you are completely disorganized in terms of field. This is the 1/3 of all the three we measured before, and we can compare this with this value of the magnetic field of the imaginary part of chi3 at equal to 0. You see you have essentially the same value. So our assumptions here seems to be not so bad. This we are sure that we measure this. This is an assumption, but this assumption seems okay, indicating that this possibility of same values of imaginary part in the two other axes are not so different. They are different from the parallel condition. And the hyper-Rayleigh scattering, as I told you before, we measure this intensity in second harmonic, the intensity of the incident beam. This is a geometrical parameter. This is the number of observers or emitters. And this beta here is what we got as information. So if we plot, don't look this is not so important, is the E2 omega as a function of E omega. Okay, so it's a parabol behavior, but you can plot E2 omega over E square omega as a number of, the number of observers here. So you have a straight line that must pass through, near the zero here. This is not exactly zero because you have the solvent present, okay? Okay, the solvent must be water or the nonpolar fluid. So because of this, it's not exactly at zero. But with this line here, you can have beta. And we can measure beta in the magnetic field and electric field perpendicular or parallel. So we will see the anisotropy of this hyperpolarizability. These are the results. Equal to 0, H0, H different from 0, parallel. H0, H perpendicular to the electric field. You see, we don't have many difference between them, but here, yes. In this condition here, with respect to the perpendicular, you have an anisotropy of about 70% in the first order hyperpolarizability of the sample. Here's the field we use it, but not important here. So this anisotropy in the hyperpolarizability of this type of aggregates, so ferrofluid in the presence of H, is about 70%, and chi3 very high, 55%. So gives us a very interesting possibility to use this in applications, because this is related to the nonlinear optical absorption. And this is the hyperpolarizability of this object when you measure with the electric field in this direction or in that direction, okay? Well, so the take-home message we can have this magnetic nanoparticles. Oops, sorry. Oops, go back. The magnetic nanoparticles, if you are in the presence without the magnetic field, you have the diffraction here, so the N2 is negative. So gives a characteristic of the lens, divergent or convergent. Here is a divergent lens. This is the value of it. Beta is a nonlinear optical absorption. The beta as a function of H here. You have the hyperpolarizability here. This is nonlinear absorption. This is hyperpolarizability. And when you have H different from zero, you have the formation of the small linear aggregates, and essentially you have this anisotropy I showed you before here, which is an anisotropy of these aggregates with respect to the nonlinear optical properties, chi3 and hyperpolarizability. So I hope you have an idea what we are doing in this nonlinear optical properties of magnetic nanoparticles. Thank you very much, and I absolutely open for your question. Thank you very much for your attention.
And very much informative talks today. If there is any question from the participants, they can type it so that I can convey the message to the professor in the chat window. So I think the people are requesting to unmute them. So I will unmute. Wait. Wait.
Well, if someone wants to make some questions, written something, please send to my email or to Anup. You can send me these questions. I'll be happy to respond all of them.
Ramesh Mishra sir, are you there? No. 1 minute. I am unmuting and looking the way how to unmute. Please wait. Speaker. Okay. Unmute party. Okay. Okay, you can ask the question. I unmuted all.
Hello, sir. Hello. Hello.
I am here.
My voice is audible?
Yes, you are audible.
Thank you, sir. Very nice talk, sir. I have some query. Right? Hello.
Yes, you can ask.
Sir, that is Z scanning techniques is based on the Rayleigh scattering technique, Rayleigh scattering method.
The Rayleigh scattering is essentially a linear process. So when we measure the linear observance, usually you measure the extinction. You make the beam here, the sample there, and after you measure what passed through the sample. We name this essentially this extinction. Which process may have in the middle here? You can have, depending on the intensity of the beam, if you are using a very low intensity of beam, so you have linear absorption, but you can have Rayleigh scattering also. If you have particles which are aggregate, you can make the Rayleigh scattering. So to measure the real absorption, you have to make a model for the Rayleigh scattering, which is a and you remove this from the extinction, you have the real linear absorption. This is used to tune exactly which energy of photon you will interact when you put a high intensity laser. Is it clear?
Okay, thank you, sir. And next question, sir, what is the phase separation of the nanoparticle? Means phase separation around.
Yeah, the phase separation occurs. There are two reasons for phase separation. If you put a high enough magnetic field, when the particles go together, if there are some damage in the layer of amphiphilic molecules attached to the particle, if they are removed for some reason, the particles can attach. If they attach, they will no more be possible to make them apart. So you can have a phase separation there.
So that
Another
means,
possibility.
okay, that means nanoparticle are also two polar and non-polar molecules, just like polar and non-polar molecules.
No, we put amphiphilic molecules. Amphiphilic molecules is a polar head and a non-polar chain. Okay,
Yes.
so this type of particle of a molecule that you attach to a particle. You have a particle here, for example, you have an amphiphilic molecule with the polar head here and the amphiphilic part, the non-polar part there. So you attach this to a particle, okay? And after that, you put another one with the chain, and the polar part will be outside this big particle with double surfactation. This type of particle you can put in polar solvent, okay? If you
Sir,
want to
you
put,
okay, sir. You have
yes,
synthesized the different type of nanoparticle, such as cubic, spherical, and spinal structure of nanoparticles in your laboratory.
yes, we worked with particles of from 2 nanometers until 50 nanometers of typical diameter or the size of the square, from 2 to 15.
Okay, sir. Thank you, sir. Sir, last question. Sir, that is hyperpolarizability is the special condition of the nonlinear effect. So, what is the special condition?
Well, this
Polarizability and hyperpolarization.
yes, this is the hyperpolarizability of a particle, okay? Of the particle of the Fe3O4 that we measure. So when you shine with a very intense electric field, this particle, this hyperpolarizability, so the modification of the electric polarizability occurs there. It's not magnetic polarizability. We don't change the magnetic property.
That is electric polarizability.
Exactly, exactly. Yeah.
And sir, this is critical magnetic field 1 and 2 means, sir, I cannot understand the critical magnetic field.
Ah, this is,
H1C and H2C, I think you have explained in your PPT slide.
yeah, the first, no? One of the first. This was measured not only by us, but by different groups, is what happened when you put a magnetic field in a ferrofluid. So the low field, when you see in the X-ray, you see that when you increase the strength of the field with the X-ray, you see the formation of aggregates. So this is an information of it depends on the ferrofluid. It depends if it is ionic ferrofluid, surfactant ferrofluid, if it is in water, if it is in oil. It depends a lot of chemical parameters of your material. But what we saw, we and other people there, is that when the field is very small, so the thermal agitation of the particles is enough to avoid the formation of aggregates. But after when the field increase, you start to froze one direction, so the dipole-dipole interaction, okay, will try to make lines. So in the X-ray, we see that.
That is basically depend upon the alignment of a magnetic field at a particular.
Yes. The strength of the magnetic field.
Yes.
The direction is always fixed. And after
Thank you,
that,
sir.
if you increase more these lines which are formed, make these bundles.
Yes. Thank you, sir.
Very
Thank you, sir.
Very nice.
Many more questions on the. There are many more questions on the chat window. I will spell out one by one. One fellow, Dr. Kalmini, is asking that what are the tools used to analyze the non-linear effect of light signal. I think you already explained.
Yeah.
They discussed. So I think. And another question is what kind of laser is used for Zscan measurement?
What is pardon, it's very badly connected.
What kind of laser is used for
The
Zscan?
laser, yeah. We have different types of lasers here. And the one we use in this condition is chameleon laser from Coherent, which gives femtosecond pulse width. Okay, femtoseconds, and we have a different frequencies, and the lambda is about 800 nanometers that we tune observing the linear absorption. So we go to the linear absorption, we see where the linear absorption does not occur, okay, because we are not interested in linear absorption. So the cross section for linear absorption is very, very low. But if you put enough intensity, you are able to have this two photon absorption. So it's a coherent chameleon laser. If you go to the site of coherent, you can find this chameleon there.
And
Okay.
another, yeah, okay, thank you, Professor. Another question is, what is the use of two, I think, detector D1 and D2?
And two,
D1 and D2. What is the use of two? I think detector is the detectors, D1 and D2. I don't understand this question. I think I have to move forward. Does D1 measure alpha, D2 measure beta parameter? One fellow is asking.
oops, problem. Please repeat.
Sir, I think that is D1 and D2 are two detectors. Hello?
There's something there. Try again. I suggest you send me.
Hello. Hello.
Hello. You hear me? Did you hear me?
Hello.
Yes,
Sir, I have a question. Yeah,
Okay.
sir. What type of changes in nonlinear properties of a sample when the dimension of sample is going to reduce?
We don't know. We believe that is a quantum confinement. So when you confine this structure in a very small object, which has not only the crystalline part in the center, but a amorphous part in the shell, because all these particles are core shell particles. They have a core which is crystalline, and they have a shell around all the particle where the spins are not oriented. So probably due to this kind of interaction between this non-oriented spin part around the particle and the crystal, it could change the electronic structure there. We don't have more explanation for this. We just saw that there is a different number, and the only thing which is different between the bulk material and the nanoparticle is this shell around and the size of the particle. Because of this, we are guessing that we are seeing something related to the quantum confinement, the modification of the electronic structure due to the size of the particle. But this is basically speculation until now. We just have the numbers, but we don't have models to see how we modify this structure in a small structure compared to the bulk. It's a speculation, certainly. We just have the numbers until now. Okay. Anup, I can hear you. Anup, I can't.
Okay, now you can hear. Yeah.
Okay.
One fellow is asking, this is last question, I think so. I think for Zscan, the material should be in collateral form or crystal form or solid form, means for performing such experiment of Zscan. What should be the state of material? Means any kind of state will be okay.
For the Zscan,
I mean liquid or solid.
It can be solid. For this Zscan I described it today is the transmittance Zscan. So the sample must be transparent to this light. But there is also a reflection Zscan. Okay, so you can use for reflection also.
Okay, thank you, Professor. If anybody is having a question, please email to Professor. I think he's a very famous person. You just type his name and you will get the email. And also he has mentioned his email in his slide. So in future, any audience, any participant can contact to Professor Neto.
Okay.
And will answer you the questions. And thank you, Professor Neto. I will keep in touch with you. And I owe you a lot. And you very much nice talk today. And see you in future.
Okay.
I will keep in touch.
Sure.
So I am ending this session right now. Yeah, bye, Professor.
Bye-bye. Bye-bye.